Log on, tune in, find out. Another good idea from Cambridge.
To the afternoon session. We have a couple of speakers, and the first speaker is Paul Spicer. Well, the program says he's from Sydney, but it's not. He's from Leuven, we stole him, and we're happy to have him. And he will be talking about a discrete system from the recurrence coefficients of two variable elliptic orthogonal polynomials. Please, Paul.
Thank you, and thank you to the organisers for giving me the opportunity to speak here. Now, my talk today is about orthogonal polynomials and discrete integrable systems. Pardon? Oh, crap. Alright, okay. Begin again. My talk today is about orthogonal polynomials and discrete integrable systems. However, unlike the conventional approach, I will be using formal orthogonal polynomials. So I will not be stating any type of weight or deformed weight function. I'm beginning with part one, where I'm going to highlight that connections between formal orthogonal polynomials and integrable systems already exist in the literature, though perhaps some people are unaware of it. Basically, what I will be doing is constructing the three-point recurrence relation that's associated with orthogonal polynomials, and showing that as a result of this derivation, you end up finding an integrable bilinear equation. Then, using the whole idea as a template, the second section, we are looking at creating a new class of two-variable orthogonal polynomials, where the two variables are related through the Weierstrass elliptic curve, and then following a similar approach as in part one, we will derive some recurrence relations and show how you also get a similar equivalent system of bilinear equations. So to begin, I'm just introducing some standard notation for orthogonal polynomials. So I've got my orthogonality relation up here at the top, where the only, which is pretty much all kind of standard stuff, the only point that I have is I tend to deal with monic orthogonal polynomials. So the leading coefficient is 1. So you can calculate that just using the orthogonality relation, that a three-point recurrence relation satisfies these orthogonal polynomials simply by putting x into either side, using this expansion, substituting it into either side, and you can find some kind of general expression where the Sn and the Rn are as of yet unknown. You can then find the Sn and the Rn again by using the orthogonality relation, and it's very simple and it's very straightforward. However, from the point of view of integrable systems, it's not very interesting. So the method I will describe is interesting, though considerably more complicated, which is probably why not a lot of people use it. So another general property of orthogonal polynomials is that we have C, which is defining the moments. Yes, the moments of the weight function is defined as the C. The reason I introduce the moments becomes obvious on the following slide, because the whole approach for finding this three-point recurrence relation is to define orthogonal polynomials in terms of a determinant, and then you apply a determinant identity to the determinant, and this leads to your three-point recurrence relation. So first of all, you either need to know that Pn can be represented this way, which you can find, it's in Sager's book and it's in Bateman and Adeli as well, or you can derive it just by setting up a Gram-Schmidt orthogonalization, and it only takes about a couple of pages to do. This expression is slightly different to the one found in Bateman and Adeli, because that one is for non-monic orthogonal polynomials. So some of the terms will be slightly different, but on the whole, it's pretty much the same thing. We also have this expression for the Hankel determinant delta n over delta n minus 1 is equal to hn, where hn appeared in the orthogonality relation. So we now have our determinant for orthogonal polynomials. We now need our determinantal identity, which is this one, the generalized Sylvester identity. I call it the generalized Sylvester rather than just the Sylvester identity, because every time I tend to come across the Sylvester identity in the literature, they always tend to throw the 2x2 form at me, which I just think is what can be often conventionally used. But the whole thing derives from this more general expression where, well, the 2x2 form is about removing 2 rows and 2 columns, always keeping your determinant square. The general one involves the removal of multiple rows and multiple columns. So for this first part of the talk, I'm only dealing with the case where we have m is equal to 2. So I'm just sticking m is 2 into this thing, and I get this nice expression which reduces to this. This is a graphical form of, actually this is not directly related to this, but I've interchanged some rows and columns. But just a note on the notation here, basically what I'm doing is the black lines, I don't know how clear it is down there, but the black lines indicate the determinant and the red lines indicate which rows or columns are being removed. So in our second one, we're removing first row, first column, last column, first column, first row, last row, and so on and so forth. The reason I write it this way is when you're working it out, at least in the more complicated cases, it just looks a lot nicer rather than looking at this whole thing. Anyway, the next step for this methodology is we have to introduce adjacent orthogonal polynomials. So whereas the standard orthogonal polynomials have C0s, C1, C2s, etc., all the way up to Cn, it's necessary to introduce a upper index of m so that when we're applying our cutting of rows and columns, we're not constantly introducing lots and lots of new objects. So it's pretty much we're just basically taking our polynomials orthogonal with respect to a shifted weight in this instance. And then we're applying different cuttings of rows and columns to this determinant. Where since in this instance we're trying to get an x recurrence relation, we will always wanting to be remove the first column, since this is the only column that does not contain an x in the bottom. So the two arrangements of the Sylvester identity that we settle on are these two. So we fix the rows and the columns are the same in both instances. The only difference is in this one we've lowered the row to the second to last row. The reason we choose just these two is this is the only arrangement of rows and columns that will not introduce new objects. If we put them anywhere else, we would get entirely different Hankel determinants popping up, and we're trying to keep things as simple as possible. So when you apply this cutting of rows and columns, you get the following two recurrence relations, and then it's just a simple case of combining the two. So I've just written it for simplicity in the following form. I've defined everything in terms of Q and T, where Q and T are defined as follows. Then it's just a simple case of increasing the top index by 1, plonking it in the second one to eliminate the x, gives us this expression. Multiply the whole thing by x, use the top expression again, we'll simplify it to this, and then you just need to lower the n index by 1, and you get the following expression, which is the well-known 3-point recurrence relation, monic recurrence relation, where our recurrence coefficients are now defined in terms of Hankel determinants. Now, it is then possible to reduce, to simplify this equation even further by applying the by applying the Sylvester identity to one of the Hankel determinants. Again, you can consider many different possible types of rows and column cuttings, but at the end, this is the only one which produces an identity which only contains the deltas. Otherwise, new objects are thrown in. And when we use this relation, we can simplify the form of what becomes our S, which is this bit here, and we can simplify our equation very nicely to R, where we now have R essentially defined in terms of delta n delta n minus 1 divided by delta n minus 1 over delta n minus 2. And going back to our original definition for delta n over delta n minus 1, we find this is just equal to hn over hn minus 1, which is what you get when you work out this method using the orthogonality relation. Now, from the point of view of orthogonal polynomials, this is about as interesting as it gets. And since it's easier to work out this relation just by using the orthogonality relation, most people, apart from the perspective analysis, would not have any dealings with it. But from the perspective of integrable systems, we pay more attention to the relations that pop out, such as this one. So this relation, on closer examination, turns out to be very similar, at least in appearance, to a special case of a discrete time-Toda equation, which is stated there. Now, it's not identically the same, as you can tell from the lower indexes, but it's fairly easy to ratio one in towards the other. Alternatively, you can use the recurrence relations derived before to find a lax pair, and when you look at the compatibility between these two lax matrices, you find out that this pops out as a consequence. So already we're looking at just the formal level of orthogonal polynomials without even having to look at any kind of weights or anything like this, and we're already seeing some kind of example of an integrable system popping out. So we thought that if this happens in the standard case, what happens when you try something a little bit more complicated? So we decided to have a look at orthogonal polynomials over an algebraic curve. So there's a book by Suetin which is talking all about the interesting things that are going on with two-variable orthogonal polynomials. In particular, where the two variables are related through a curve. I think the most advanced case they ever got to looking at was on the unit circle. And if you're just exploring these things for the interests of what possible curves you can go through, there are a lot of choices before you even get remotely close to something as complicated as the Weierstrass elliptic curve. However, we were not building it from the interests of orthogonal polynomials, but from the interests of integrable systems. So what curve would be interesting to use, which could possibly create interesting integrable systems? So we decided to go with the Weierstrass elliptic curve. And unlike in the previous case, where our elementary monomials were all of the same order, 1x, x squared, x cubed, so on and so forth, we now have in two variables, x and y, and our x is of order 2 and our y is of order 3. This obviously has the knock-on effect that E1 does not exist whatsoever, which obviously causes some complications later on, but there are ways of dealing with these troublesome people. Anyway, so we can. So this is the sequence of monomials that we have associated with the curve. The only other thing that I point out at this instance, if you're trying to find a recurrence relation from a sequence like this, if you wanted to find something with just x in it, you would have to eliminate 1, y, and that would be it. If you wanted to find a y recurrence, on the other hand, you have to eliminate 1, x, x squared, and then use the cube, the curve, to bring in the y squareds, which just adds a little bit of complication. Anyway, so moving on from that, that's more of an orthogonal polynomial point rather than a the net integrable systems point. Anyway, moving onwards, we, having set our orders for our x's and our y's, we wanted to see what the size of the x relation and the y relation would be. And we find that the x relation will now be 5 points and the y relation is 7 points. So already we're moving into a more complicated sense than the standard 3 point that you have to deal with from general orthogonal polynomials. So we have our 5 point and our 7 point, where at the moment our recurrence coefficients are totally unknown. And then there's some initial conditions should you wish to generate these. But the difference, of course, is that x and y are not independent of one another. They are in fact related through the curve. So strictly speaking, if you can find one recurrence relation, you can find the other just by making use of the curve. And you can write the recurrence relations as the following pair of commuting difference operators associated with the y-strapped elliptic curve, where we would also expect that such a system might provide a discrete analog of the Khrushchev-Novikov system, but that was more of a passing thought. We never really managed to explore whether there was anything in that. Anyway, so we're now trying to set up our, we're trying to derive our recurrence relations, so we find it necessary to express our orthogonal polynomials as determinants. However, as I mentioned at the beginning, there is the slight problem of the fact that E1 does not exist. So if you set up a determinantal identity similar to the one that we had in the first case, where these are all our moments, then we automatically get a problem the minute we set L is equal to 0. The minute L is equal to 0, we have a whole row that does not exist, the E1s. So we find it necessary to introduce another polynomial determinant, EQ, which solves this little problem for us, and where we set Q0 equal to PK0, and similarly for the Hankel determinants theta and delta. So if we now stick in the value of L, L is equal to 0 for the PK, everything shifts along next to the Q's in the sense that, so this would no longer be E1, this would in fact be E2. Anyway, so we are now looking for a recurrence relation, as we were doing with the initial situation. And this time, as I pointed out, we need to remove the 1 and we need to remove the y. So we find it necessary to bring in a 3-row column. More than 2 rows and columns. We have the 3-row and column removal, which is this thing here. So it's actually simplified somewhat from this, since we can cancel the squared with all of the determinants of a's on this side. But basically, when we expand it, we get a determinant with 2 rows and columns removed and a determinant with 1 row and column removed, where we're fixing our columns to eliminate our 1 and our y, and then a back one for stability, so we keep square determinants. And yes, so this is what we get from this. So, and then your rows and columns, well, your columns are fixed, but your rows can interchange. But at the end of the day, you're always trying to limit things within your new objects. But since we have P and we've already introduced Q, we do have a bit of flexibility with it. Anyway, just a little add, this little dash in the middle is just indicating that there is a gap. So it's not the removal of several rows in the middle of the determinant. So we're removing the first column and the third column. That's all that little line is indicating. So this relation here is basically what you get when you apply this to the PKL relation. And you can do lots of these. You can find many different types of XPs and XQs. You can So, but you're always, like I say, you're always trying to limit your choices. Now, to make a recurrence relation, you need another relation involving p's. If you're trying to get an xp, it doesn't really help if you've got q popping up all over the place. So we then have to go back to 2 by 2 Sylvester identities. Now I note that I haven't actually told you what t and pi are explicitly, but they're basically the p with the first column and second to last row removed, and similarly for the delta. It's essentially the 2-row column. It's what you get out of the 2-row column when you apply it to the p. And you get the following two linear relations in p and t, which you can combine. You can make use of a similar Hankel identity here. Combining the two leads you to this nice little linear relation in p. And then you can use this relation with this relation to give this relation. So yeah, it's fairly straightforward. You multiply the whole thing by x and substitute different things in. Anyway, this is what you can do from an orthogonal polynomial interest. But again, we're kind of interested in what kind of relations pop up from the bilinear setting. So, so first of all, we thought, okay, we'll apply some cuttings of rows and columns to the Hankel determinant, delta, and we find this relation here, which turns out to be, in fact, the only relation you can get by just directly applying a cutting of rows and columns. You can find this relation, but it involves combining about 3 or 4 of these different things where new objects are constantly popping up all over the place. I didn't really want to describe where that comes from, but it basically involves doing 2-row column cuttings on deltas and thetas of different sizes. Some new objects get introduced, and then you can eliminate them, so it's just in favor of the deltas and the thetas. You can then combine these two relations to get a single relation in terms of delta. And this is an 11-point quadrilinear equation. Now it turns out that this 11-point quadrilinear equation has a lax pair, which you get by setting phi equal to the following and making use of this relation and this relation. So you can construct a lax pair from these two relations, which looks like this, and the compatibility between these two laxes is satisfied for this relation. So now we managed to find some kind of strange large object here, which we until this point have been unable to classify, but it's something that we are currently working with now. And that's the end of my talk. Bit of an abrupt ending, I'm sorry.
Okay, any questions?
Yeah, so in your first part you had these relations for the adjacents of polynomials.
Yes.
I think they are well known except for those expressions, these coefficients.
Yeah, no, my point.
Coefficients of deltas.
My point is that most of the, I'd expect that most of the first part of what I talked about is already known. It's just, I don't think most people are aware about it. That's all.
So, Alexei Zhujanov has developed a certain amount of theory related to biorthogonal functions, and again, you get second-order recurrences, as it were, which is basically what you have with the 3-term recurrence and some stuff like that. And there's, in certain special cases, there is again that sort of structure we were talking about in the first part. So it seems like it might be worth trying to develop a similar sort of thing for just non-symmetrical elliptic functions, but where instead of just hitting the identity a whole bunch of times,
Yeah.
you pick some sequence of points and you hit in that sequence. There should still be recurrences and still should be this sort of compatibility relation.
Okay.
Okay, let's thank the speaker again.